fewer students than usual today. I hope they're just coming in. As opposed to my scaring people away. We left off, I did a hurried introduction to HTTP 2 at the end of last class. There isn't a whole lot to say about HTTP 2 and 3. 3 is not really out there yet, or it's kind of getting there or just there. But 2 has been around for longer. We saw in the previous class that HTTP 1.1 compared to 1.0 primarily adds persistent connections. Persistent connections allow you to pipeline HTTP requests. They allow you to send a bunch of GET requests and allow the objects, the corresponding objects, to stream in back to back, instead of having to open a separate connection, one for each object. That's what 1.1 did over 1, right? Persistence is what presentation did. However, this is the 1.1 still has some performance problems. The server responds in a first come first served manner, which results in a problem called the head of the line blocking problem, or HOL problem. We'll see this problem a couple of times. In chapter 4, for example, when we look at router fabric design, we'll again see this problem occurring. What's the head of the line blocking problem? It refers to the problem of the request not being able to be processed because of something else that is ahead of it in the queue. Sometimes there are resources to process this object, but simply because you're forced to do everything the first come first served manner, because the scheduling policy says so, you have to wait until this object is processed, even though this could have started getting some resources also. If there's any losses in any of these objects, it's going to stall the whole pipeline, because everything is flowing in this pipeline manner. And so HTTP 2, the main thing, it adds a few things, but the most important thing is it allows for object interleaving. Okay? So that's the last bullet in this slide. Divide objects into frames, schedule frames to mitigate HOL blocking. This is the most important performance optimization that HTTP 2 will use. It also has some other features, handy features. It allows objects that are unrequested to be pushed or prefetched to the client. Sometimes it's useful for a client to have objects that it doesn't know it is going to need very soon. Normally, a client is going to fetch the HTML base file, look for inline objects, and then send those requests. But if the server already knows that 99% of clients are going to send these requests anyway, it's handy to be able to push, or from the client side, prefetch these objects before they are actually needed, or actually come to be noticed as needed. So that's another performance optimization. And then the second bullet, transmission order of requested objects based on client-specified object priority. So that allows, that also mitigates the HOL problem somewhat. Prioritization rates. Instead of just being restricted to the SCFS first come first served scheduling discipline, more important objects can be placed further ahead of less important objects. So if you want the rendering of the web page to show the most important stuff first, instead of everything waiting till most of everything has been downloaded, this is handy as well. So because of all these features, you see web pages becoming more and more user-friendly and responsive. You don't see a blank page or stalling for a long time. You'll probably see some activity. Sometimes part of the web page starts rendering. Sometimes the most important stuff starts rendering, and then all of it to get rendered takes a little bit longer. So these are all enabled by HTTP 2. Here's a picture to keep in mind. The part that's shown here, pipelining of GET requests, multiple outstanding GET requests, they're getting pipelined. This is there in HTTP 1.1. This is what persistence allowed you to do. In 1.0, we would have only one outstanding GET for a connection. Then we tear down the connection, spend an RTT, establish an import. We're not doing that in 1.1, right? So far, so good, but this is the HOL problem. If there's a large media file for which the request goes out first, then all the other smaller things are back behind it. Even though the user might be happier with all the smaller frames being rendered, and maybe a large media object is just there, they may not even click play it to start viewing it, but the whole thing is stuck behind a big object. All the small objects are stuck behind the big ones, right? How do you get around this problem? Well, you have to place one option is to decide where to place this big object, right? If the client could specify priorities, maybe you could say get the small objects first, big object later, okay? But then again, you can't change this decision midway. It's not always easy to rely on prioritization alone. So you really need interleaving of objects. So that's what HTTP 2 is introducing. It's going to send these objects in this manner, interleaved manner. So now HTTP is beginning to look almost a little bit like a transport protocol, like TCP. TCP also segments data and sends data in different segments. So HTTP is slowly maybe I should just move less. Or try moving less. I don't know. I hear a background hum that sometimes increases in resonance. Do you, right? I don't know what exactly causes that. Right. Let's try standing still and talking. So this interleaving of objects allows us to get around this HOL, header to line blocking problem. It starts to look a little bit more like feature creep into transport level functionality, a little bit like breaking the clean modularity between transport and application layer, right? This is segmentation at the application layer, breaking objects, larger objects into smaller segments, right? So if you have this kind of pipelining, after all the smaller objects have been sent, if there's nothing else to do, only the big blue object frames, they'll all get sent back to back at the end, right? This is more desirable where all objects are getting some progress over time rather than facing the HOL problem. So that's HTTP 2. Object prioritization, pushing or prefetching of unrequested objects, and most importantly, interleaving to get around the HOL problem. And there's a lower level implementation differences, status codes and things, but they're more detailed, right? There's yet another new kid, HTTP kid on the block, and that's HTTP 3. So what does 3 do over 2? Well, 2 is already fixed. 1.1 added persistence, 2 allowed for interleaving and getting around HOL problems. But that doesn't still solve all of our performance and security related problems. So HTTP 3 does even more of a feature creep into transport level functionality. In fact, it explicitly allows for support for a transport protocol called QUIC. That's the word QUIC without the K at the end, so QUIC, QUIC. That's a new transport protocol. This was developed by Google. It came out of Google. And it's at a 10,000 feet level, it's a little bit like what you'll see in your second programming project, which is build a reliable transport protocol over UDP, which is an unreliable datagram or transport protocol, right? We haven't yet seen the transport level section, so it will be harder to appreciate really what QUIC is, why it's desirable, and it would be a distraction to go too deep into that right now. But long story short, HTTP 3 basically adds support for a protocol like QUIC, as well as the equivalent of HTTPS, which is TLS support, transport layer security support. It's inbuilt in HTTP 3. Right? So we're increasingly moving towards just encrypting everything instead of HTTP for clear text and HTTPS servers for encrypted data. Well, not just encryption, but the whole TLS code may include authentication to the server and encryption. Okay, so let's look at some clicker questions. This is a fairly simple one, so take 20 seconds. Close to 100, so we'll wait till, let's say 85 and then count down to 5. So everyone got this one right. That's true. There's nothing tricky about this question. Okay. We'll wait for 85 responses. Five, four, three, two, one. Okay, so there's only one correct choice. About 2/3 of you got it fine. I think reducing the number of connections. That's really all there is to persistence. Persistent HTTP connections pipeline HTTP GET requests. They don't reduce the number of requests. They send the same number of requests. Persistence and pipelining, however, are slightly different concepts. Okay, so let's take a moment to understand the distinction in between. You can have one without the other. Okay, persistence just refers to keeping a TCP connection open. Pipelining is about being able to send multiple outstanding requests. So if you had, let's say, a base file of size S0, okay, and let's say the body of that object contained, this is the size of the base file. Let's say this is all there was. There's a web page with n images in it. Okay. The base file is a size S0, just a few bytes, and then the size of each image is just S. Okay. And there's n of these images in the page. Do I see a hand there?
Yeah. You're kind of like
Oh, sure. Thanks for. Is that better? Yeah. Maybe I'll try to write it bigger. Size of base file is S0. Size of each of the n inline objects is S. Okay. If we used HTTP 1.0, how much time are we going to take to download this file? How do we answer this question? Anyone? We're going to go a few questions back. A few slides back. We're going to keep this picture in mind. So with HTTP 1.0, you got to form a TCP connection. That's one round trip. So that's the first. Go to the right, come back down to the left. That's just establishing the TCP connection. And then there's one more round trip for just one more round trip that I advised you to think of as simply the time required to fetch the first byte of the response. So the first portion of this blue response, that's at least one more round trip, because request has to go in response. It's the first byte of the response has to come back. The longer the response, the more the transmission delay you're going to incur. So we need one more parameter here. So we already have n. N is defined right here. Let's assume this capacity of this channel is C. So we'll call this transmission. Right. So how long will HTTP 1.0 take? It's going to take at least one RTT. We also need RTT. T is the RTT, that's it. Okay. So it's going to take one RTT for the connection establishment, one RTT to fetch the first byte of S0, and then transmission delay for the entire S0. So that is equal to 2T, that's 2 round trips, plus S0 over C. Is this all the time for the whole web page? No, this is only the time for the base file. At this point, the client has fetched the base file. Now it knows, by looking at the base file, that there is n inline object URLs, each of which it has to fetch. How much time is it going to take to fetch each of them? It's going to incur a very similar cost for each one of them. For every single object, it has to do the same thing. It has to form a TCP connection. That's one T, and then one more T to send the GET request, get the first byte, and then fetch the object. So that's HTTP 1.0's time. Does that make sense? Does that correspond? Right? Fairly simple. Just we're making sure that this corresponds to our understanding of how 1.0 and 1.1 work. Right? We're quantifying the performance benefit, or we're trying to in the process of quantifying the performance benefit. Okay. What does 1.1 do? 1.1 adds persistence. And it has support for pipeline. What is persistence? Persistence means don't close the TCP connection. Keep the TCP connection open. Okay? So, in order to understand, like I said, the distinction between pipelining and with pipelining and without pipelining, let's first look at the without pipelining case. Okay? Just persistence. If all we added was persistence, we will still get a benefit. And that benefit is going to be 2T, or the download time with 1.1 with just persistence will be 2T plus S0 over C. This part is not going to change. You've got to spend this much time to get the base file no matter what. You've got to format at least one TCP connection, and then one more to get the first byte, and then the transmission delay. However, for the inline objects, each of the n inline objects, you don't have to incur this cost, the first T, to fetch, to set up the TCP connection. You just get and get the response. So for each of the n inline objects, you have only one T plus S over C. Assuming that you send a GET request, get the response for the first inline object. Then send a GET request for the second inline object, get back the response for the second inline object. After you've gotten the complete second object, then you send the third, get the whole third, then fourth, and so on. That's persistence without, because it doesn't say anything, that's without pipeline. I'm looking at this case, I'm showing this case to you only to clarify the distinction between persistence and pipeline. They're distinct things. Okay? 1.1 supports both. 1.1, now let's look at what happens with, alright, this is too much at the bottom, so I'll move. So with pipelining, well, persistence and pipelining, you still have to do this part every single time with all the HTTPs. There's no getting around this, right? You gotta first fetch the base file before you even know what else to assemble in the web page. I'm stuck. I don't know what to do. Is this working at all? If I just hold it like this, as opposed to this, yeah, it makes some difference, right? All right, I'll just try doing this and hope that in a few minutes this goes away. So like before, I'm just going to let this be on here because I think I have a suspicion that what's that called? Echo 360 works only when the microphone is on and it's catching something. So I'll just keep this on. I realize it's not working, but that's driving me crazy, and I guess you guys too. So we'll just work with this. I'll try speaking louder, okay? And we'll hope that these days don't occur as frequently. Okay, so this part I said always remains the same. This is the base file. For fetching each of the inline objects, you got to do, n times the work. What is that work per inline object? With pipelining, you can send all of the requests, all of the GET requests in one go. Okay? So in fact, I wrote this too soon. After fetching the base file, in one round trip, you can send all of the GET requests, like in back to back. These GET requests are very small, so they don't cost us any transmission delay. Let's just assume. Yeah, GETs are very small. So you have sent all of the requests. You incur one round trip for the first byte of all of the responses that are streaming in. That's this round trip. There's no TCP connection now. This is just the GET request and the first byte of all of the responses that are coming in. For each response, you have this time, S over C. All of the responses are streaming in. There's no magic. You can't get more than C bandwidth out of a pipe of capacity C. So if there was only one file, you take S over C. If there's n files, ns is the total number of bytes, and C is the available capacity, so this is the total transmission. So that's the difference. Here, you have 2T times N. Okay. Without pipelining, you still have half of that. You have T times N. But with persistence and pipelining, you have removed the NT dependence entirely. There's no dependence of the overall download time on N times round trip. N does appear here because transmission capacity is limited. There's no getting around that. But you're not adding some either one round trip or two round trips per object like you were doing in one of these cases. That's the big win in 1.1 over 1.0. I see a hand there.
Would it be like two extra round trips and get extra data, like transmission time for the user to ask the server what files do you have for the server transition and the user?
The user doesn't ask the server. When it gets the base file, it looks in the base file for what inline objects here.
Oh.
That's exactly the information contained in the base file. That's the whole point of the base file. Yeah.
So does HTTP automatically provide consistent pipeline, or does it have to be like configured on my server?
if you're using 1.1, it'll automatically support persistence with pipelining. Okay. I separated with pipelining and not pipelining only to illustrate that they're two distinct concepts. You can have one without, you can have persistence without pipelining. It doesn't make sense to talk about pipelining without persistence. That wouldn't make sense. You can have persistence without pipelining. It's persistence, it's a combination of persistent connections with pipelining that gets rid of the order n times t component. There's no n, 2nt or even nt. There's no product of n and t occurring in one form. Okay? Alright, so next question. Is the one with it? This is the one with it. Alright, 5, 4, 3, 2, 1. Oh, there's some diversity of opinion here. Among the following, which case you get the greatest improvement in performance with persistent compared to non-persistent? Low capacity network paths, high capacity network paths, long distance network paths. It's clear that there has to be a dependence on distance because we're saving round trips, right? Persistence is saving, is changing this 2nt component to just 1t. So the longer the t, which is long distance network paths, the more you will save. The savings from going from 2nt to t are going to be more if t is high, right? That doesn't depend on, so C is a potential candidate answer for us here. But how does it depend on capacity? Does it depend on capacity at all? So I would say, if I look at the performance improvement as the difference in time between this quantity and this quantity, this has ns over c and s0 over c. All the c terms simply get cancelled out. If you look at it as a difference, there's no dependence on c. The most reasonable interpretation of this question would be the difference. So I would say c is the right answer.
Wait, how would it be faster if you're sending over a longer distance?
In which case you get the greatest improvement. Yeah. How would it be faster? Because the difference is 2nt minus t, and so the difference is 2nt. But it doesn't happen deterministically. Like right now, it's not happening.
I think it's getting close to the speaker.
What?
I think it's getting close to the speaker.
Oh, the speaker is there. I see.
The big.
Oh, so if I'm on that side, it's likely to work. Let me try that. I can just use
Who's that speaking over there?
the speaker there. Okay. I don't know if that's helping. That's the difference. Okay, this difference depends on T. The higher the T, the more the difference. And so the more the benefit of HTTP versus HTTP, okay? Does that clarify? Whoever has a question? I take silence as affirmation. If you look at it as a ratio of this divided by this, there will be a dependence on C. And so, if you have really high capacity pods, the C parts would, these components would go down, the RGB component would grow. So really high capacity pods, if you look at this as a ratio, high capacity pods, long distance pods is where you get the most benefit. If you look at it simply as a difference, it really depends, it's not dependent on C. The difference is how I would interpret it if the answer is C. I hope it clarifies for whoever asked why that was. All right, let's try to do this quick. Five, four, three, two, one. But strictly respecting SCFS rules, okay, this is good. So let's go back to the features we added. Okay. The answer is not C. The answer is potentially non-SCFS order. Why is this? Let's go back to the slide on HTTP 3. I'm sorry, HTTP 2. Things, so interleaving, yes. So it's one of C or D, right? It allows for interleaving, but it also allows the client to specify priorities, object priorities. The client may send requests in whatever order, but may specify that these objects are more important, and so they will circumvent the FCFS policy. Yeah.
Which one is called?
Oh, is that, sorry. Which of the following is false? Okay, sorry, thanks for that. I'm not even doing it. Breaks up, sorry, let's go over the choices again. Breaks up constant stuff. This is true, speculatively suspicious, this exists in HTTP 2. Strictly, okay, so this is the right answer. Okay, sorry about that, my bad. Thank you. That's the false one. Okay, web caching. Last quicker question in this session. All right, your hypothesis. Yeah. Reasoning sources. I saw a few of you just not even trying to do this question, okay? So I assume that this needs clarification for why the answer is whatever it is. It says P is a fraction of requests that's captured in the cache, so that's the hit rate. Okay. What's the average delay contributed by transmission delays alone? There is no queuing for each object. Your average should be expected delay. That's what it means. Expected is technically better term than average. What's the transmission delay? How's the transmission delay computed? Size of the object divided by speed of length. Okay. It says here already, ignore LAN transmission delays, and essentially it says ignore queuing, or it says transmission delays, of course, doesn't include queuing. So it's a parenthetical reminding you that don't worry about queuing. So on average, there's 30% probability that you get the object in the cache. So in that case, all you have to do is get it from the cache over the LAN. LAN transmission delays are zero. Says no, LAN is very fast. So in that 30% of cases, when there is a cache hit, there is no transmission delay, essentially. We'll pretend in this question, right? In the 1 minus P probability, so it's basically transmission delay is P times 0 plus 1 minus P times for each object, it's going to be S over C. That's the transmission delay for each object. It also says there's no queuing, so that's it. This is the expected transmission delay. Is there a choice? That's choice C. So that's it. So it's not this. This is simpler than the problem we saw in class, right? The problem we saw in class it accounted for missed delays. It accounted for a few more things: the wide area round trip, it accounted for queuing. So if you forgot that, a few slides back. There, go back, look at the previous lecture, and it'll make it much clearer. This is a much simpler version of that problem. Okay, shall we move on? We're going to look next at SMTP and DNS. SMTP is a protocol for email. Simple Native Transfer Protocol is what it stands for. We're all familiar with email as users. One of the most bread and butter applications on the internet as well. There's 4 major components. There's a user agent, like Mac Mail that I use on my Mac. There's any number of email clients out there. These are user agents. These are things that run on your phone or your laptop, desktop, on the endpoints. There's mail servers with which these user agents interact. The mail servers speak a language that's called SMTP. That is what is SMTP. There is an agent server protocol from my laptop to a mail server. That's generally IMAP or POP, POP3, version 3. It could also be HTTP. We'll look at some of how this works in a little bit more detail in a second. The user agent is what's running on my machine. Okay, you're all familiar with probably your iOS or Android mail client, or Outlook, or Mac Mail, or Thunderbird, or any number of mail. Just simply mail on the command line on the Unix shell. That would be your mail client. Mail servers are the things that speak this SMTP protocol. SMTP is a client-server protocol. There's always a client and there's always a server. It's a push-based protocol, so when somebody sends mail is sort of activated because of somebody sending a mail, right? You don't ask for an email from somebody. The mail starts by the act of push. So SMTP is a push-based protocol, unlike HTTP. So when the mail is sent, the sending side SMTP server is going to push that to the receiving side SMTP server. And the protocol you speak in order to do that is simple mail transfer protocol. They contain mailboxes for those respective users. Outbox here, inbox here. And the spec of this SMTP protocol, like all the other protocols you've whoever initiates the push is the client in this case. Right, the sending mail service side, there'll be a handshake, underlying protocol is TCP, which is of course one of the library protocols, just like HTTP. There's a transfer of the email messages, and then closure of connection. It's also a readable, human readable, and therefore human typable, speakable protocol like HTTP. Right, so here, let's totally look at what happens when you send an email, and then we will speak the email protocol. Just like we did HTTP on the command line using Telegram. If Alice wants to send an email to Bob at someschool.edu, she's going to use her user agent to send this message. It's going to be placed in her school or her institution's mail server. That acts as the SMTP client. It establishes a TCP connection with Bob's mail server. So the mail server at someschool.edu pushes this mail that Alice sent to Bob, which is stored in Bob's inbox until Bob connects to that mail server at some possibly future time. It doesn't have to be synchronous, and retrieves this message. So we are familiar with how we use email, right? It seems intuitive. It just seems like the most intuitive setup for how email must be working underneath the covers. And really, there's not too much more to this besides protocol implementation level details. Let's look at how this SMTP interaction happens. So that's an example of how the sending side SMTP server is speaking SMTP with the receiving side server. So this thing is speaking this protocol with Bob's email server. A typical opening command that's part of this handshake between the server and the client SMTP server and the server SMTP server is a hello message that's spelled with one L. It is what it is. So we're going to try speaking this protocol. I'm going to switch to the command line. We're going to tell it to the CS mail server. Now, what I'm going to show you is it can be used as an email prank. Be careful while experimenting with this. Impersonating somebody else, it's a crime. You can get into serious trouble. But I'll show you an example of how you can speak SMTP and send email that looks like an email that came from somebody else. Why? Because we know how to speak SMTP. Now, this is most easy to show on the command line, like manually speaking this protocol on port 25, which was the first email protocol port number. But port 25 emails are not encrypted, they have no security in it. So a lot of people don't use them. A lot of email servers simply block port 25 because they don't want to be unencrypted email anymore. They want email to be encrypted only, right? That's on a different port. And there it's much harder to show this. I would have to do a bunch of things like he said. It's just not worth it, right? Not much pedagogical value in showing this. Some email servers, I tried this before class, so I know this, that the CS mail server doesn't like people on port 25 trying to do this if you're from outside UMass or outside CS mail. So I'm going to SSH into my desktop. It's called FIG. And I'm going to do it from there because it succeeds from this. Okay. Now, you can try reproducing this by searching for a mail server that allows port 25 connections. So here's how we're going to, what's Telnet? It just gives you a TCP connection, just a TCP connection, nothing else. Whatever you type is all that's being sent from that connection. So that's our CS mail server. How do you find out the mail server? Well, we're going to look at DNS shortly and you can find out what the mail server of some domain like UMass.edu or CS.UMass.edu is using DNS. Okay. So I'm going to connect on port 25 because I don't have Telnet on that machine. I was pretty sure I tried this and it worked. There we go. to switch back and forth because I know what's there on the slide. So I'm going to say, this is basically telling the other server, hey, I'm CS or UMaster with you. Actually, I should have probably said UMaster with you. This is not going to matter what greeting, what I announce myself as is not terribly important for this to show. Alright, I'm going to just go to my email client real quick. I should have removed all this. Sorry, we're reading my email now. That's too many. Probably violating protocol laws. Alright. So what do we have? Yeah, that looks like an innocuous email from DoorDash trying to sell me food. That's the state of my email inbox right now. It's not terribly important for you. In fact, the less you can read my mailbox, the better it is. But the point is, that's the state. And I'm going to send an email and show that I can receive it. I'm sending this email to myself, okay? So I'm not committing any crime. I'm not impersonating. Or I'll show you how to impersonate somebody, but I'm just sending it to myself. Okay? So we say mail from, what's the from address, okay? Let's see, what's your email address? One second. BIT? That looks good? Okay. So here it said, okay, if you try this from outside CS or outside UMass, I don't know which one. I think outside CS, it won't like it. It'll snap back with an error message. It used to work, but like I said, increasingly people are trying to just block 425 entirely or limit the kind of thing they can do. Okay, so at this point I've said, I have an email from Oshabit. Her name is Omri. Omri, I'm pretending to send an email from Omri to myself. And when we are ready to type the email, we say data, that's the command. So I'm going to say, I don't know, I'm just pretending Omri has a message like this to send to me. Alright? And then, I don't know, he also says hello world. Right? And then some gibberish, some more gibberish. And the dot on a new line, like here, is the terminator of the message body. So it says happily the CS mail server queued. Okay? So here I have an email from Oshabit saying, showing you what I just typed. Yeah.
Shouldn't mail servers have authentication for that? Like,
425 doesn't have that.
425 doesn't have authentication?
No. So if I go to my mail server settings, I see that by default I'm using these port numbers. Oh, sorry, not this one. CS yeah, I forgot where it was. It is I think the port number is 493 or 445, something like that, 400 something. That's the encrypted SMTP port. You can look this up online.
So just to be clear, like, are you pretending to be a client sending an email to the server and the server delivers it to the mailbox, or are you
I'm-
pretending to be the server itself?
I'm pretending in this example to be an email server
Oh. But then
to the CS.email server.
yeah, wouldn't, DMARC, SPF and EK block,
Wouldn't what block?
SPF and EK and DMARC?
I don't know what those things are. What is that?
Oh, those are like records, or like, mail servers allowed to send. It says like,
Oh,
which IP
so-
address is allowed to send.
Right, so if I tried this from my laptop, for example, there's this depends entirely on what the administrator managing the service is, right? So here it showed you a success. That's, oops, sorry, wait. So I'm going to now try the same thing from my laptop, okay? And it will not work is my guess, because when I tried this earlier, it didn't work. And I'm connected right now to the Eduroam network, so I think that's what I tried with. So we're going to try the same thing. Maybe it's going to work.
Do you mind like showing the email errors for that email?
There is no headers. Remember that all we have is a telnet connection. What I typed is literally all that got sent. I can of course make this email, so this thing didn't work, but actually when I tried it before class, I got an error message right after receipt, but it seems to have taken. It's not giving me these okay messages, so I think it's just being snappy. So nothing really worked. I'm gonna try this once more. It already closed the connection at some point. It never established a connection. Okay, so that's what's happening. It never actually established a connection. Alright, so this seems to not even accept a connection even outside CSS. So those things you can configure, those are not part of SMTP. Those are firewalling policies that administrators can specify on the machine to accept or reject connections. They may also be embedded deeper into the application itself, right? SMTP requests of this kind filter them out and so on. But SMTP itself on 425 is just clear text. So anything you send on 425 is clear text. So your ISP that's carrying your traffic, they can see your email if it's on 425. You got a question?
So your desktop computer works because it's on CS stuff. What does it mean to be on CS?
Good question. So the CSW master EPU is a set of, it's an IP address prefix. So it's a prefix of the kind 128, 198, 154. An example of a prefix. CS prefix is just wait till chapter 4 to know what a prefix is for. Notation. But it's a group. It's just like you have domains, CS, master EPU, master EPU. You have IP address blocks or prefixes associated with those domains. And so it's fairly, because everything is going over IP, you look at the IP address to see who the source of the sending site is, and firewall policies.
So the computer itself is labeled as a CS, like something in CS network, or is it the network that it's on?
The IP address assigned to the host is part of the address block corresponding to the host. Again, this will become a lot clearer further, a little deeper in this stack. Right now we're at a very high level. You're asking the right questions, but we just haven't covered it. You understand the depth. Okay, so I just showed you how to connect to an email server. So I pretended there to, this is the SMTP. SMTP is a protocol between servers. So I pretended to be another SMTP server talking to the CS, mail.cs master EPU SMTP server, right? Some of them may allow you to send email to addresses beyond, other than their clients. They may allow you to originate emails from other servers. This really depends on what they're configured to allow or disallow, right? You may not find a server that allows you to actually do this. But from inside the department, you should be able to reproduce exactly what they show. I saw hands.
Is there a command to, because you have like a data line, so that you can have your like body of text, is there a separate command to do like the subject?
Yeah. Oh, sorry, I meant to add that. this obviously looks like a fake email, right? When you look at something like this, you kind of become suspicious. It has no subject, it has no header. You can add all of that, right? This is all part of the email SMTP protocol. You can add all of this information. I can make this email look genuine, right? You can also write a program like Python, PHP, whatever language, high-level language program. You just send hundreds of emails that are spoof emails that just look legitimate. Right? There's no way to distinguish between legitimate and you can make them look as legitimate as well. Because everything is underneath is using the same protocol. So whatever your email client can do, you can program that. Right? This was just an example to show like how easy it is to just send it to spoof. Yeah. Louder. Oh, I can add that. I can add your full name here to show as well. Did you say OSH? Yeah, yeah. Your name.
Yeah, but,
This. It won't say anything. Well, I've only said, if I actually wrote down your name like Omri Shabit and then wrote your email, it would show up like that. If I added a subject, it would show up with a subject. I can, like, again, keep in mind that literally what I type is all that's being sent. There's nothing more. So you won't see it. That's the reason you're not seeing more. Alright, so let's move on because we spent quite a bit of time on this. Play with it all you want. Don't abuse it. You're the best judge of what's abused and what's pedagogically beneficial. Okay, comparison with HTTP. Really just a push versus pull is probably the most important difference in SMTP and HTTP. Just because of the nature of the application, so clients and HTTP are requesting objects, servers and client side and HTTP is requesting objects. Client side SMTP server is generally pushing something, right? They're both ASCII. So that's why I can speak them. If they were binary encoded protocols, it would be much more cumbersome. I don't have a way to type binary characters on my keyboard. I would have to write a program to speak them, right? But they're both ASCII protocols. SMTP is 7-bit ASCII. It doesn't use all 8 bits because when you have MIME encoded bodies or attachments, then you use that 1 bit to say whether it's encoded or not. So that's why SMTP can have binary objects as attachments. It allows multiple objects to be sent as part of a multi-part message. In HTTP, each object has its headers. Each object is a separate entity. It has its own headers and its own response. But in SMTP, you can have a multi-part message. So that's, for example, you can have a body and a few attachments. That's like a multi-part message. Each email itself has each email itself has headers, right? You've seen from, to, date, and so on. These headers are, these email headers, which are mostly absent in this prime email, these are different from the mail from, receipt to. These are part of SMTP. So this mail from and receipt to supply the information that gets put in the body of the email message, or in the header of the email message, as from and to information, right? So those headers are different from these commands. They're connected in that they're semantically. And then a dot on a new line is basically a terminator. At the end of message terminator in SMTP. Right? In HTTP, we didn't have a terminator, right? For requests, we had a new line, an empty line. So character return followed by new line. But for response bodies, how do we know what's the terminator? How do you know when the response body ends in HTTP? We have in the headers a content length. So that tells whoever is the receiving side, starting from the point where headers end, which is a new line, how many bytes of response constitute that whole object, right? So it's part of the header information. SMTP doesn't encode it that way. There's an explicit terminator message, right? So these are implementation details. Yeah, I think it's very obvious when you do this. The user agent protocol, that is the language that the user agent that's running on my machine speaks with the SMTP server. That's not SMTP, that's a different protocol. The most popular protocol these days for that is IMAP. Earlier it used to be POP3 that was less user-friendly. IMAP allowed you to keep state. The IMAP is a protocol that allows you to maintain folders, drafts and outbox, and you delete a message that comes from one machine. If you go to another client and look at your email there, everything will seem synchronous. It won't look like a new email all over again, right? So all of this state is being managed with this IMAP protocol. HTTP is also a client, an end client to server protocol for email. However, the way it actually works, it's not like you speak HTTP with an email server. But when you go to a browser like gmail.com or gmail.com, look at your email, you're obviously using, because you're using a browser, you're using HTTP to speak to the Gmail server to look at your email and do all the operations like deleting or creating folders, saving, and whatever you do with email. But that protocol from your machine to the server is of course HTTP, it's going to a browser. But on the server side, there's an HTTP front end to the SMTP server, that's the Gmail server. So HTTP is often used as an end to user agent protocol. But behind it is generally an IMAP protocol that sits in between HTTP and the SMTP server. That's the Gmail server. So in that example, it would be HTTP, IMAP, and then SMTP. Right. Okay. POP is just like a previous generation protocol. It's increasingly less and less used these days. Just because IMAP has much better features with folder organization, state maintenance, and so on. All right. Questions about SMTP? Email? Anything outstanding before we move to DNS? DNS is often described as the telephone directory. In the phone world, we have names and numbers, right? So these days, yellow pages are, yeah.
With the period being a terminator symbol of SMTP, does that mean it would be impossible to just send a message including one period?
You have to escape it. Anytime you have these special characters that you want to use outside of its usual meaning, you have to escape it. So backslash is often an escape. So you can, but it needs to be encoded accordingly. So DNS is often described as telephone directory of the internet. Back in the day, when yellow pages, these telephone directories, giant books were a thing, that was your database, right? You would get these periodically in the mail, delivered by whoever provided you your phone line service, that map names to telephone numbers. DNS does something similar for the internet. It's mapping domain names, like www.cs.umaster.edu, to IP addresses, which are like the numbers. Names to numbers is very similar, comparable functionality. Instead of telephone numbers, we have IP addresses. So that's the problem DNS is solving. It's a distributed database, so it's geographically distributed. It's not at one centralized place. And it is an application level protocol. So in the 5-layer stack, application transport network link physical, it's at the topmost layer, an application layer. It's different, it's special. It's different than any other application. It's a special kind of an application because even though it's an application, it is fundamentally to the functioning of the internet. Pretty much everything you do starts with a lookup to DNS first. So even though it's designed as an application, it's very much part of the infrastructure of the network. It's not like HTTP, SMTP, Facebook, or Firefox and whatnot. It's as much of the complexity of the network's edge and endpoints is sort of inside the network. This is one of the design philosophies of the internet, keeping the core of the network as minimal as possible. Okay, what does DNS provide? It provides more than name to IP address translation. Name to IP address translation is the most bread and butter canonical service. It provides other things like host aliasing. So what name as an alias with whatever name, there's multiple names that can be used for the same server. One of them acts as a canonical name, the other is an aliases. You can find out what the mail server is for some domain. I'll show you how exactly to do that. It allows you to also load balance or distribute load across replicas of the server. So if I go to my command line and NSLOOKUP is a common command for name server lookup. DNS command take is another popular command line command for DNS. So if I go into www.google.com, okay, it gives me, no, it only gives me one address. Usually it gives me more. Oh, that's fine. So it gave me this address 172.217.165.142. So let's try. Oh, sorry. Yeah, that's the address it gave me. So let's see how far this Google server is. It's only 12 milliseconds away. I must be really lucky. I'm so close to Google, right? But in reality, that's not what's happening. www.google.com is replicated at 100 plus locations in the world. I'm just being redirected to one that's fairly close to me. Okay. So you try this from anywhere in the world, you'll probably find a Google web server within 20 milliseconds. It's very unlikely. You have to go to a very remote part of like Siberia or something, or Antarctica, to not be within 20 milliseconds of a Google server. Okay, so why is this happening? I'm going to stop this. This is happening because one function of DNS, load distribution that's on the slide, that's being activated. When I query the DNS server that's returning me the addresses, it is distributing load in a manner such that clients are redirected to servers nearby. So that's how it's doing that function. So it's not centralized, I told you it's a geo-distributed database. Makes sense to distribute it, right? Centralization introduces a single point of failure, single point of congestion or load. It just becomes harder to maintain a centralized solution. It's less secure, you're protected to one place in the world to bring down the entire internet, because if DNS doesn't work, nobody remembers any IP addresses. Hell, nobody even remembers phone numbers these days, but certainly nobody remembers IP addresses of services. They also keep changing. They also change more often than telephone numbers people change anyway, right? So that's why you want to use a distributed database approach. And DNS is a distributed, hierarchically organized database. That hierarchy looks very like shown in the slide, and it's very intuitive. At the top level is a domain called dot. So when you see an when you see a DNS domain like umass.edu or cs.umass.edu, implicitly there's a dot at the end, so it's cs.umass.edu dot. That highest level dot is the root of the DNS naming tree. It's not explicitly used, but that's the best way to think of it. A dot is a root of the entire DNS tree. From there, you have .com, .org, .edu servers. These are called TLD or top-level domain servers. The namespace can keep on branching out like a tree further beyond that. So UMass is and then inside UMass is CS or UMass. Inside CS or UMass, we're a college. We right now are one department, but the idea behind coming to college a few years back was to have multiple departments within the college. You may eventually have, CS and informatics within CICS and so on. So the naming hierarchy naturally resembles the real world hierarchical organization of these organizations. If a client wants an IP address for, let's say, www.amazon.com, it's first going to query the root server. It's gonna go to the very top and figure out what's the address of the .com server. It's gonna then call the contact the .com server and then ask it, where is Amazon.com? And then it needs to know www.amazon.com. So it's actually going to go to Amazon.com authoritative DNS server and know what Amazon.com's web server is. www is just the web server. There will be other email servers, and lots of other servers at Amazon.com. Right? That's the hierarchy. The root are not, even the root is a distributed database. It's not a single machine thing. Okay? There are 13 logical root name servers. You can query this in NSLOOKUP. You can say type equals root, and it gives you a list of 13 name servers. That doesn't again mean there's only 13 physical machines out there. Each of those 13 is an IP address that corresponds to a root name server, but each one of those IP addresses is replicated at multiple places. So there's basically hundreds of root name servers. It's incredibly difficult to bring down the root. People have tried this. They've successfully sometimes DOS, denial of service attacked, or brought down through other malicious ways, one or two of these root name servers, but rarely succeeded in having, by attacking the root, being able to bring down the internet. It's incredibly hard. It's just engineered because it's hundreds of these servers distributed across the world. ICANN is an important organization. That's the Internet Corporation for Assigned Names and Numbers, right? So if you want a website, let's say you wanted the name whitehouse.gov, G-O-V. You cannot get that name because whitehouse.gov is owned by somebody else, right? That's the rightful owner. That's considered by much of the world as the rightful owner of that name. Sometimes disputes can arise. Some people may indulge in the business of park domains, where they might buy a domain just in the hopes of making money from it later because they think that something was wonderful, right? Some of this is legal, some of that can border on the illegal. There can be sometimes disputes between who's the rightful owner of the domain. So ICANN is the body that's ultimately in charge of both the root name, managing the root of the internet, as well as name adjudication, who's the rightful owner of it. Okay. DNSSEC allows, now provides authentication integrity. It's not as widely used as it should be used. DNSSEC adds security on top of DNS. It allows you to verify that the server you're speaking to is indeed the server you think you're speaking to. The root is redirecting you to the TLD server and then to the authoritative name server. You're visiting different servers. You better know for sure that you're indeed talking to the server you think you're talking to, as opposed to a man in the middle pretending to be that server, capturing your packets and then pretending, sending your responses, pretending to be that server. DNSSEC will allow authentication and message integrity that prevents such kinds of attacks. TLD servers, these are examples, .com, .edu, and then country level domains like China or UK, France, Canada, Japan, and so on. The textbook I think still says Netflix Solutions owns .com. It's not VeriSign for a few years now has owned the .com domain. These TLDs are businesses, corporations, institutions, organizations with domains. Okay. VeriSign may sell the .com domain to somebody else. It's the most popular domain out there. If you want a .com name, you indirectly are you're registering the name to VeriSign registry, and VeriSign is making some money. So there's a market for it. People, VeriSign bought it in that market. You can just sell it to somebody else. Yeah.
So I can make money from the .com.
Yes and no. ICANN is not a non-profit organization, international. Until some time back, it wasn't making money from top level domains, but recently, like 5-6 years back, it allowed all these fancy top level domains like .i, .io, .apple, just ending like all of Apple computers names might end in .apple, right? Or .me for like identity based websites and so on. So for those fancier, these are called G Yeah, for these ones, I can charge this now